Today we will execute the first test of the Cice 2025 benchmark competition. So we have here the beam, and we have also the staff that is helping me on this test, Mr. Luis Manzuri, and also Rosbe, that is not okay. Hello, Rosbe, and also João, that is close to the equipment. So, well, before to starting, I'm explaining you that this beam is a strength for flexural with 3 laminates of cross-section 1.4 by 20. It is in soffit of the beam. And well, we have these lines to indicate the location of, or the position of the steel stirrups, and the horizontal line is to indicate the position of the flexural reinforcement. So during this test, we will evaluate some important results at service limit states, namely the loads, the deflection, the strain in the FRP, the strain in the steel, the strain in the concrete, the crack width, and the crack width will be the maximum in at the level of the steel flexural reinforcement, and also the average crack spacing. So at ultimate limit state, we will evaluate the maximum loads, the corresponding deflection, and the strain in CFRP. So we are ready to starting loading. So Luis, 10 seconds. Okay, excellent. Okay, so we are almost initiating. Okay, so this is the logos of the institution that are supporting this experimental program. Well, it was also a great pleasure to announce that we received 6 participants using analytical models, and 5 participants using a numerical approach for making their predictions. So, well, today we will execute the first test, and 23 we will execute second one. So, and then we will make the average of the results of the 2 beams. I don't know if I told my name, so I'm Joaquim Barros, and I'm coordinating this competition. Okay, so the load is, okay, we have already started. We will announce the loads. So Manzuri is marking the cracks and the corresponding loads when obviously the cracks appear. So I should remember that we have enough stirrups, steel stirrups to avoid shear failure. So we are expecting a flexural failure mode. So the load has already started. So we have the IC system here to have a good prediction, or to measuring with accuracy the crack spacing and crack width. I remember that crack width will be evaluated at the level of the flexural reinforcement. So up to now 30 kilonewtons. So we have 30 kilonewtons at this moment. The test is being in displacement control, so it is controlled by an LVDT that is internal to the actuator, and the velocity is 20 micrometers per second, 40 kilonewtons. I'm going to the other side of the beam, where we have the LVDTs. So we have the LVDTs to measure the displacement. So we have one in the center of the beam, 2 in the loading sections, and 1 in the middle of the shear span. Uh, well, we are also measuring the the strain in the concrete. So you see, so we have a strain gauge on the top to measure the strains in the concrete, and we have internally. So do you see in the bottom? So we um, we have the the strain gauge that are bonded to the CFRP as well to the steel.
Okay, load.
The first crack is happened
70.
70 kilonewtons.
Load.
Okay, so Mansour is fixing, is indicating the load. 74 at this moment, 74.
Load.
77, 77. So this is, as you can see, is a flexural crack. So in between the loaded sections,
Load.
we have 80, another one, another flexural crack, 80 kilonewtons. It's progressing to the top. Okay, returning to my explanation. So using the strains in the top, in the concrete, and also the strains in the steel, we are able to evaluate the curvature of the cross section, and this is an important indicator together with the moments. So using the moment curvature, we can estimate what is the evolution of the flexural stiffness. Now the load is 87 kilonewtons. Do you see the crack spacing is quite nice, is almost equal. 90 kilonewtons at this moment. So apparently we still have okay, secondary cracks. Do you see now a 90? We have a secondary crack. Okay. So in the DIC zone, obviously we cannot see the cracks, but obviously we have also cracks in this zone. So 95 kilonewton.
Load.
95. Okay, kilonewtons. 95. Okay, good.
Load.
Another secondary crack, as you can see, 97 kilonewtons.
Load.
100. So the first crack in the shear zone, but obviously it is flexural, it is almost vertical. Okay. I remember again that we have several steel stirrups to force the flexural failure mode. We will see if the laminates will attain the tensile capacity in the failure of the beam, and if it will happen, this means that we will mobilize the total capacity of the CFRP laminates, which will be very nice.
110.
110, so some more secondary cracks. 110 kilonewton. Okay, so another crack here in the shear zone, but again it's still the
150.
150, 115. So okay, 117, 117. Okay,
Loads.
so 33. It will be nice to verify if the existing analytical models and design guidelines are able to predict the crack width and crack spacing. Mainly crack width is quite difficult. It's even very difficult to estimate the crack width using, well, fine element models, mainly those using a smear crack model, because the crack width in the smear crack model is the product of the strain normal to the crack multiplied by a certain characteristic length. We have some difficulties still, some difficulties to estimate this characteristic length, to avoid the results be dependent on the mesh refinement. This characteristic length is dependent on the geometry of an element, but we still have some difficulties to have a good predictions in terms of crack width, and even on the strains in the materials. So 145, we see here inclined crack. So this is a shear crack, but I'm confident that this shear crack will be controlled by the stirrups. Okay, so 150, 150, 150 kilonewtons. Okay. See? Yes. Well, the test will be, I suppose, more 20-25 minutes. 155. Okay. 120. Well, according to our predictions, so 169. When the CFRP bars will fail, so we will have a drop on the load carrying capacity, and this drop is corresponds to the loss of the CFRP contribution, and then we will have the load carrying capacity provided by the steel bars, and then so we can interrupt the test because we have already attained the maximum load. So this means that we have the information corresponding the maximum and corresponding the flexion and also the strain in the CFRP, and then we don't need to continue. 170, 170, 170. Okay. So it seems curious. So this shear crack now.
Load.
Now. So it's aligning along the stirrups. So the stirrups are being effective to control the propagation of the crack. I remember that we have also a phase that we designated by crack propagation stage, so when we have several cracks forming, but at a certain moment we attain what we designated with crack stabilization stage. This means that no more cracks will be formed, and then the crack width will start concentrating in the critical crack. A new one, okay, so you see a new one, a new crack in the shear span. So it seems that here we have a maybe the critical crack. It seems that the crack width is being concentrated. You see, the crack seems to open more in this crack. This one also, so it is 195. 195. Okay. At a certain moment, the crack will progress in the flange. In the flange, but not yet. So this means that neutral axis is still in the web. But I believe in few minutes we will have the crack progressing in the 205. in the flange 205. 205.
Low.
208. Okay.
Load.
Load 214. Okay. Another
Load.
216 kilonewton. 220. Well, it seems that we are attaining the phase of crack stabilization.
Load.
224.
Load.
226. Okay. Now, yeah, so
Load.
now finally the crack is progressing in the flange. So we have two main cracks in this zone. Is half of the pure bending zone, because the other part is being occupied by the DIC.
Load.
237 kilonewtons. No, this the 240. The exactly now this crack is progressing through the flange. So the incline crack has attained also the flange, or is attaining here. So we see is inclining now, is in the interface between the web and the flange. This crack 250 kilonewtons. 250 kilonewtons. Okay. So the 255. So
Load.
some ramifications and the cracks that are formed in the shear span. So now the crack that is closer to the middle span is progressing. Load to 58. So it's progressing through the flange. Well, the crack opening is clearly increasing. 259. So this is a new crack in the shear span.
Load.
The opening here of this crack is also
260.
significant. Okay. The participants can start checking their estimatives to see how good were the predictions. Well, but obviously we are still loading. 263 kilonewtons. Okay. 264. I will go to the other side, but in the other side we are not being able to see clearly the cracks, but thank you, Luis. But we see here the cracks, you see. So this is in the shear zone. So, and now these are the crack in the loaded section, and now in the zone considered in pure bending, is in the pure bending zone between loaded sections. So we see the flexural cracks. So the distance is very clear. So it's very clear, the distance between the cracks, and we see that apparently this crack has the highest crack width, but we will see if it will degenerate it in the critical one. We will see. I'm coming again to the other side where we are marking the cracks to 72. 272,
Note.
274. So a new crack is progressing on the flange. 274. 275. So the increment of load is now much, the gradient of increase is much lower. So because the stiffness of the beam is much lower due to this crack propagation. We will provide the force deflection relationship when we conclude the test, and this will be very visible because we have up to the crack initiation the behavior is elastic. Then we have a second branch where the stiffness is decreasing, but in general smoothly, and these phases correspond to the crack propagation up to the moment where the longitudinal steel start yielding. And above this stage we have the contribution, mainly the contribution of the CFRP laminates. At this stage the longitudinal bars, steel bars, are already yielded. Obviously they continue to make a small contribution because the steel has some hardening, so they provide some contributions to increase the load, but this increment is marginal comparing to the contribution of the CFRP laminates. 282 kilonewtons. So we see relatively large crack width in this in the crack that is at the loaded section, but the other two cracks have also significant crack width. So okay. So it seems that now 295, that the main cracks are already formed. Now it is the propagation of crack width in the major cracks and the propagation of the cracks towards the top of the beam. So the neutral axis is going up, up. So we see here the cracks in the shear span seems totally controlled. The crack width seems not increasing. So the crack width seems to increase in the pure bending span in between the applied loads. The contribution of the laminates is significant mainly after the yield initiation of the steel. So we are approaching to 300 kilonewton.
Load
292. Okay.
load
294. I remember that this test is being controlled and displacement at a velocity of 20 micrometer per second. 295 kilonewton. So the crack width in this crack is larger almost in the middle of the web than at the level of the reinforcement due to the tension stiffening effect.
load
296. Okay, as you can see, the cracks in the shear span has a certain inclination
298
due to the principal stress orientation. So the crack is progressing to the top to 98.
load
298. Okay, to 98. João seems to indicate that the load is in a plateau at this stage. So the crack width is larger in this flexural crack. So as you can see clearly, the crack width is larger. 299. So the crack is now progressing. The load is now, the increase is now very slow. 299. 300. Okay. Good.
Note.
302 is a new crack close to the support. Since the load is increasing, obviously the cracking moment is close into the support, and then we have the formation of cracks when the principal tensile stress attains the tensile strength of the material, and this form a new crack, obviously. 305. Okay, good. 305. So this is this inclined crack that is apparently is merging the vertical one, but the cracks in the shear zone, clearly the crack width is stabilized, so it's not increasing. What is increasing is the width of the main flexural cracks. So
Note.
we can see in the BIC window also the flexural cracks, and the space is very clear and very similar, so the distance between cracks, which means that we will have very good information in terms of crack spacing. 310. Okay, so the crack is progressing to through the flange. 3110. Okay, so do you see this a relatively large crack width? I believe that now we have more than, I think, 1.5 millimeter of crack width, apparently. Okay. 312. 312 kilonewtons. Uh, 314. Okay. 315. In the shear zone, seems now everything is stabilized in terms of crack propagation, and now is the moment where the main flexural cracks are progressing. They are in competition. Who will be the one where the that corresponds to the failure one. We expect that the the laminates that are crossing these primary flexural cracks will fail in tension. If this happens, this means that we are mobilizing the total tensile capacity of the laminates. 319. Okay. I will try to show the at a moment to show the bottom. Okay.
No. 319.
Do you see? So we have the okay. Thank you. 319.
The cracks have been failure or
Hmm?
it's already been dangerous.
No, I suppose that we are still far away, a little bit. Yeah, yeah. So when we'll be approaching 350, so I will give orders to that is our excellent collaborators do not continue to to mark the cracks because start being unsafe. So we see the very large crack width. Mansour Erosbe, in few seconds, I think it will be better to interrupt this operation, okay? Because it will become unsafe.
322.
Okay, 322, it's only more. When we will attain 330, we will interrupt, okay? You need to leave this zone.
Three. 24.
Okay. It seems that in fact the crack in the loaded section is the one where we have the highest crack width.
Load. 329.
Okay, it's enough now. It's enough. It's enough, okay? It's enough. Now, due to safe reasons, so because the crack width is very significant, it seems that is about 2 millimeter in this zone. So now it's recommended to leave this zone, and well, because also now the propagation of the cracks is mainly in the critical one, so it does not make any sense to continue to mark the cracks because the relevant cracks are already formed. So we have eventually the propagation of the main cracks to the top of the beam, but I will try to show you in the bottom. 335. So the load continues to increase. I'm going myself to a safer zone. Okay, now I'm a more distance from the beam. Okay, so we see so the the crack width is localized, or the opening is seems to be concentrated in the crack in the low section. I hope that we the bond conditions of the laminate be good enough to mobilize the tensile capacity of the laminate. So I'm good expectation about it, but we will see in some seconds, because I think that we are approaching the failure load. Okay, so as you can see, inclined cracks, but the crack width concentrate despite this crack. This crack in the shear zone, the crack width is also significant. Okay. Load 342, 342. Okay. 'Go around on the beam. Well, okay, so it's also very clear the cracks, so the inclined cracks in the shear zone, and then, well, in the pure bending branch, well, we see the the flexural cracks. 345, 345. It is also visible the deflection. The LVTs are supporting aluminum bar. This aluminum bar are supported in the alignment of the supports, and to avoid to record spurious deflection. So we are only measuring, the LVTs are only measuring the deflection of the beam. 348 kilonewtons. 348 kilonewtons. Three hundred and fifty. 350. Well, so I believe that the participants that have met, so now can check their prediction. So because the load is not too far away of the ultimate load, this is my impression based on the the crack width. I imagine that those that have estimated crack, ultimate load, well, closer to 400 kilonewton are hell praying that the beam is capable to support some more load. To be honest, I don't remember the, the predictions, but I realize that it's in between 3 and 20 up to 400 something, which means that's, well, not bad. 3? 55, 55. Mhm. Okay. Now is waiting up to the moment where the CFRP attained the tensile capacity. So since the crack width in the soffit of the beam is very high, locally the laminates are having a very high gradient of strains, and consequently the tensile strain is already very high. We will see if the laminates fail in tension only in only one main crack, or if it will be possible to have simultaneous failure. We will see. So 360. Okay. Oh, for you, what was your prediction? 34. 34. Hmm. Okay, so, well, João, load. 63. The crack width is very, very large in the loaded section. It's amazing. I'm almost at 2 meter distance, but I think the crack width is more than 3 millimeter or 2.5, something like this, more or less, in between 2 and 3 maybe. 65, 365. So the question is that, is the beam able to attain 400 kilonewton? Okay. Some question or not? No, no questions on, no, okay.
Someone just asked if we are still loading. Yes, we are still.
Yes, we are still loading. Oh, it's amazing. Now this crack in the shear span, 67. 67. This crack in the shear zone has now, the crack width has now increased significantly in the last seconds. Do you see? Wow. Okay. Yeah, it's increasing significantly in the middle of the web. It's increasing, in fact, significantly. The crack is in between the existing two steel stirrups, and have two ramifications in the bottom.
What was the load?
370 something. 370. 370. Okay. Wow. Some spoiling, spoiling in this crack in the shear zone. So it's in fact opening significantly. This means that the contribution of the laminates is significant. So the load um, is in fact very high, and so this 375. So this incline crack has already crossed one of the stirrups, but crossing the top. So the crack within top is relatively small, so this stirrup is not suffering a lot. And okay, the crack width of the crack in the loaded sections continue to open. It's amazing. So we are approaching the 400 kilonewtons. Some inclined cracks in the shear zone has progressing. It was not marked, but we see that it's progressing up to the soffit of the beam. Okay, the load crack continues to open. João, load 380 kilonewtons. The most complicated prediction, as indicated in the beginning, is the crack width and crack spacing. But well, I cannot indicate the value that we have measured up to now, because this will be obtained using DIC in the DIC zone, and this maximum crack width will be evaluated at the level of the flexural reinforcement of the steel reinforcement. So we indicate the position of this flexural reinforcement with this horizontal line. So the beam still survives, continue to support increment of loads, but obviously in a very, very smooth way, because at this moment, so the contribution is mainly due to the laminates, the CFRP laminates, and also some hardening of the longitudinal reinforcement and obviously to the concrete that is in compression. The tensile contribution of the steel is at this stage almost null because the crack width is very high, so the post-cracking tensile capacity of concrete is exhausted for a very small crack width. So in these major cracks, the contribution of concrete is only to one due to the concrete and compression. And so it seems that the beam will be able to attain 385. It's amazing. Wow. So in the top, in the flange, it is visible that the cracks are inclined, going directly to the support. I don't know if it is possible to see, but well, the crack is in fact progressing up to the zone where we have the load. Okay, excellent. So do you see the crack width in this crack is continuing to increase. So his hand is in direct competition with the cracks in the flexural zone. And the bending moment here, as you know, is lower than in the bending moment in the pure bending zone. Now we start having some sounds. So I believe that. Oh, and fails. Oh well, it's the end, and due to this very abrupt load decay, so we have the tensile rupture of the CFRP laminates, but we will see. So can you take? Okay, we will see. Can you? Can you? Yeah, we put in. Okay.
It is still loading.
It's still loading, but well, now the contribution is due to the existing steel flexion reinforcement. So it seems that we have, well, we see the failure of the laminates in, it's amazing, in several zones we see here, but we have also the failure in this one. So this fails in several cross sections. So the bond was incredible. So this is the inclined cracks due to the bond transference from the laminates to the surrounding concrete. So but it's amazing because it fails in several locations. So it was mobilized. Okay. So, well, we will hand, so many thanks for everybody to attend this test. So, well, the next one will be in Thursday. Thursday we'll have the second test. So, well, I hope that you can participate in this second test. Many thanks for your presence, and well, we will be together next Thursday. Thank you very much. Have a nice day. So, bye-bye.